Science of extreme exoplanets, particularly the study of hot Jupiters and lava worlds, has reshaped our understanding of planetary diversity and the limits of planetary formation. These worlds exist far outside the environmental range of our solar system's planets, defying classical models of how and where planets should form. Hot Jupiters, for example, are gas giants similar in mass to Jupiter, but orbit so close to their host stars that their years can last only a few Earth days. Their atmospheres are heated to thousands of degrees Kelvin, sometimes hot enough to vaporize metals. Lava worlds, on the other hand, are rocky planets orbiting so near to their stars that their surfaces are believed to be covered in oceans of molten rock. These alien worlds push the boundaries of planetary physics, atmospheric chemistry, and the understanding of how solar systems evolve under extreme conditions. Discovery of the first hot Jupiter, 51 Pegasi b, in 1995, challenged pre-existing theories of planetary formation. According to the traditional nebular hypothesis, giant planets were expected to form in the cooler, outer regions of a protoplanetary disk, where volatile compounds such as hydrogen and helium could condense. However, hot Jupiters occupy orbits much closer to their stars than Mercury is to the Sun, implying that they either formed there under conditions that defy known physics or migrated inward after forming farther away. The migration model became the dominant explanation, suggesting that gravitational interactions with the protoplanetary disk or other planets caused these gas giants to spiral inward over time. Yet, this inward movement poses additional puzzles. How do such massive planets stop before falling into their stars, and what happens to smaller planets that might lie in their path? Atmospheric conditions on hot Jupiters are some of the most extreme known in planetary science. Many have dayside temperatures exceeding 2000 K, leading to chemical processes not found on any planet in our solar system. At these temperatures, molecular hydrogen can dissociate into atomic hydrogen. Metals like iron and titanium can vaporize, and clouds can form from exotic materials such as corundum, silicates, or even iron droplets. Some of these planets exhibit strong temperature differences between their day and night sides, caused by tidal locking, where one side always faces the star while the other remains in darkness. Winds in their atmospheres can reach several kilometers per second, redistributing heat and creating dynamic weather patterns that scientists study using infrared observations and spectroscopy. One of the most well-known hot Jupiters is WSP-12b, a planet so close to its star that its atmosphere is being stripped away by stellar radiation. This planet's orbit is decaying, suggesting it may eventually be engulfed by its star. Observations reveal that it absorbs nearly all incoming light, making it one of the darkest exoplanets discovered, with an albedo comparable to fresh asphalt. Similarly, HD 199733b, another well-studied hot Jupiter, has been found to have silicate particles in its atmosphere, suggesting the possibility of glass rain. The study of these planets allows astronomers to refine models of heat distribution, atmospheric circulation, and chemical equilibrium in high-temperature regimes, offering insight into both exoplanetary and stellar physics. While hot Jupiters dominate early exoplanet discoveries due to their large size and strong gravitational influence on their stars, lava worlds represent a different class of extreme exoplanets that are smaller and rocky but orbit at similarly perilous distances. These planets are often tidally locked, with dayside temperatures hot enough to melt rock and nightsides that plunge into freezing darkness. The most famous example is 55 Cancri e, a super-Earth roughly twice the size of our planet and 8 times its mass, orbiting its star every 18 hours. The day side of 55 Cancri e is estimated to exceed 2400 K, hot enough to vaporize silicate minerals, while the night side is hundreds of degrees cooler, suggesting minimal atmospheric heat transfer. Such a temperature contrast implies that the planet's atmosphere, if it exists, may be extremely thin or transient. Lava worlds challenge scientists to rethink what planetary surfaces and atmospheres can look like under intense stellar radiation. On these planets, surface rocks can melt into magma oceans, and vaporized silicates can enter the atmosphere, creating a rock vapor cycle analogous to Earth's water cycle. When these vapors condense, they may rain back onto the surface as molten droplets. In some models, the day side of a lava world may be covered by a permanent magma ocean several kilometers deep, with powerful convection currents transporting energy from the planet's interior to its surface. Studying these processes not only helps to understand extreme exoplanets, but also provides insights into the early molten stages of terrestrial planets, including Earth, during their formation. Detection of these worlds relies on precise observational methods, primarily the transit and radial velocity techniques. When an exoplanet passes in front of its star, the tiny dip in brightness reveals its size and orbital period. Meanwhile, the gravitational pull of the planet on the star causes detectable shifts in the star's spectral lines, revealing its mass and orbital parameters. For extreme exoplanets like hot Jupiters and lava worlds, their short orbital periods make them ideal for repeated observations, allowing astronomers to refine measurements and conduct detailed atmospheric studies. Instruments such as the Hubble Space Telescope, the Spitzer Space Telescope, and now the James Webb Space Telescope, JWST, have enabled unprecedented analyses of their atmospheres through transmission spectroscopy, where starlight passing through a planet's atmosphere reveals its chemical composition. JWST has opened new frontiers in the study of extreme exoplanets by providing high-resolution infrared data that allows scientists to detect molecules such as water vapor, carbon monoxide, and sulfur dioxide in their atmospheres. For hot Jupiters, these measurements help to determine temperature gradients and cloud structures, while for lava worlds, they reveal the presence or absence of atmospheres and the composition of vaporized minerals. The detection of thermal emissions from the day sides of these planets gives direct insight into their heat budgets and energy distribution. In addition, phase curve observations, tracking brightness changes as the planet orbits its star, allow astronomers to map temperature variations across the planetary surface and constrain atmospheric circulation models. Another area of research focuses on the role of magnetic fields and stellar activity in shaping these planets. Hot Jupiters, due to their proximity to their stars, are exposed to intense stellar winds and radiation, which can erode their atmospheres over time. Magnetic interactions between the planet and its star can produce auroral activity, influence atmospheric escape rates, and even affect the planet's orbital evolution. Some observations suggest that hot Jupiters may induce increased stellar activity, leading to feedback loops that further complicate their environments. Understanding these processes provides valuable analogs for the behavior of magnetospheres and atmospheric loss mechanisms in other planetary systems. Lava worlds present additional challenges in modeling because their atmospheres are not dominated by traditional gases, but by mineral vapors. These vapors have high molecular weights and complex condensation behaviors, leading to unusual temperature-pressure profiles. Theoretical models suggest that depending on surface temperature and composition, lava worlds may have atmospheres dominated by sodium, silicon monoxide, or magnesium vapor. Over geological timescales, atmospheric escape could alter the composition of the planet's surface, potentially leading to crustal differentiation and unique mineralogical signatures observable in reflected light spectra. Discovery of these extreme exoplanets also informs the broader search for habitable worlds. By studying how planetary systems produce such diverse environments, scientists refine models of planetary formation, migration, and atmospheric retention. The existence of hot Jupiters indicates that giant planets can form far from their stars and later migrate inward, which has profound implications for the stability of smaller, potentially habitable planets in the same system. Similarly, lava worlds represent the ultimate example of uninhabitable environments, demonstrating the destructive effects of stellar radiation and tidal heating on planetary habitability. These findings help to constrain the conditions under which life might arise and persist elsewhere in the galaxy. In recent years, the study of extreme exoplanets has also merged with laboratory astrophysics and high-temperature chemistry. Researchers recreate the conditions of these planets in laboratory furnaces and shock tubes to study how minerals vaporize and condense at high temperatures. These experiments provide essential data for interpreting spectral signatures and understanding the thermochemical processes at work in exotic atmospheres. Combined with numerical simulations, these studies enable scientists to build realistic models of the complex interplay between radiation, convection, and chemistry in these alien worlds. Diversity of hot Jupiters and lava worlds also challenges our ability to categorize planets neatly. Some intermediate cases blur the line between these two types, featuring both gaseous and rocky characteristics. For example, ultra-hot Neptunes and sub-Neptunes may have partially evaporated atmospheres, revealing rocky cores beneath their gaseous envelopes. These transitional planets may represent evolutionary pathways between gas giants and terrestrial planets, shaped by atmospheric loss and extreme irradiation. Observing them provides a glimpse into the long-term fate of planets orbiting close to their stars. Future missions promise to deepen our understanding of these extraordinary worlds. Space telescopes like Ariel, Plato, and ground-based observatories equipped with advanced spectrographs will expand the sample of known extreme exoplanets and provide more detailed observations of their atmospheres. As techniques improve, astronomers will be able to detect smaller and hotter planets, measure wind speeds and cloud compositions, and even map the distribution of elements across their surfaces. Ultimately, the study of hot Jupiters and lava worlds reveals the extraordinary adaptability of planetary systems and the vast range of environments that exist beyond our solar system. Science of extreme exoplanets is not merely a study of curiosities, but a window into the processes that shape planets across the universe. These worlds, though hostile and alien, illuminate the boundaries of what is physically possible, demonstrating the creativity of nature in sculpting planets under the most extreme conditions imaginable. As observations grow ever more precise and theoretical models more sophisticated, the secrets of hot Jupiters and lava worlds continue to redefine what it means to be a planet, reminding us that our solar system's familiar configuration is just one variation among countless possibilities across the cosmos.